we talked about discrete distribution. In the discrete distribution, we said there are two types that we are going to learn. One is binomial distribution. The other one is the distribution called Poisson distribution. So today we are going to look at the second type of binomial distribution. Don't forget that binomial means this is binomial distribution is two possibilities. Poisson, let's look at it is also discrete distribution, but it is not binomial. Let's look at what is Poisson distribution. Right? Poisson distribution. Let's take a random variable. You know what is a random variable now? X is a random variable, the number of success in a fixed interval. So now slightly different from the earlier case, binomial. Binomial, we say success or failure, two outcomes. Here we take success on a given interval, fixed interval. On a fixed interval, what is the success? Based on that, in another interval, what would be the success? And so on. So the number of success in a fixed interval follows a Poisson distribution, Poisson process, providing the following conditions to meet. So these are some conditions that they should meet. The first one is the probability of two or more success in any sufficiently small subinterval is 0. That means probability of two or more successive in any sufficient small subinterval. So that means if the interval is very small, right, that is what we are saying. If the interval is very small, the probability is 0. So that is what we are saying. If the interval is very small, the probability is 0. Okay, so that is the first condition in the Poisson distribution. We will see all these little later. The probability of success is the same for any two intervals of equal length. So that is the second information. That means, let's say if the success between these two intervals, let's say these are the two intervals, right? So these are two intervals. Let's say the length of the interval is x. The success of the probability, let's say it is AI. This is probability. This is probability. This is the interval. Suppose in another case, if the interval is same, suppose if, let's say in another case, if the interval is same, so I'm saying this is x, this is x, the equal length of the interval, then definitely the same probability will appear. So AI, let's say AI. So the probability is same, no difference at all. If the intervals are same, the probability also same. So that is what we are saying, right? The other conditions, or the third condition, the number of success in any interval is independent of the number of success in any other interval, provided the intervals are not overlapping. So earlier we have seen the interval, these intervals are actually not overlapping. This is one interval, this is another interval. So these two intervals are not overlapping at all. So that is what the third definition says. If the intervals are not overlapping, so the probability of this success in this interval is not dependent on the probability of the previous success, right? So these are independent events. This is independent probability from this probability. So the number of success, so that is indicating the probability, that will be independent if the intervals are not overlapping. Right? If the intervals are not overlapping, that is independent. For a sufficient small interval, the same thing that we are repeating, the same thing that I am repeating, sufficient. The first rule or the first item, the small interval. If the intervals are small, sufficiently small, then success is 0. So that means the probability is 0. Probability is 0, right? The same thing that we are repeating. Right. Let's take an example. The probability of insect damage. Probability of insect damage, right? Probability of insect damage. Probability of insect damage on region, right, of a candy. What do you mean by candy bar? Anyone? What do you mean by candy bar?
Sweet.
Sweet, yes. It is a chocolate, piece of chocolate, right? This is the, let's say you have the slab, chocolate slab, piece of chocolate, right? So candy bar is equal to the probability of the insect damage in some other regions of the candy bar. So, for example, as you all know, there will be insect, very minute insect attack to the chocolate, sweet chocolate. If you keep it outside, maybe the best example is the ants. Ants come and eat the chocolates little by little, isn't it? So the damage by the insect in one region of a candy bar, usually when you take this damaged chocolate out, you could see this piece of portions have been eaten by the insect, is it? The rest will remain same without any affection. But when you look at this Poisson distribution, the probability of insect damage in one region of candy bar is equal to the probability of insect damage in some other regions of the candy bar. So the damage, the candy bar here is same as the damage of a candy bar here, 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 and so on. Right? As an example. Yeah. Just a second. Next one, the number of success. The number of success in any random sample is independent of the number. Independent of the number. Can you all see this? Sorry. Right. Independent of the number, right? Number of success in any other random sample. So we already said the events are independent, right? So that they are not depend on one event or the other. So events are independent. Let's look at, these are some of the assumptions that we take. So let's look at the rest. We'll look at a lot of applications. Right. So this is the same example of damage to a chocolate, piece of chocolate candy, right? So this particular example has been downloaded from the internet, so that this example is from US, right? So we should understand the question clearly. A kind of organization is called as Food and Drug Administration, right? So they are the one controlling the food quality of different stores or different shops. They set a food defect action level. It's a kind of indicator for various foreign substances. What do you mean by foreign substances? If I have paddy here, I have 10 kilos of paddy. I have 10 kilos of paddy. So in addition to paddy, usually what are the things that is already inside the paddy? You have stones, isn't it? You have stones. Maybe you have some mud. Can you get all these inside this 10 kilos of paddy? Yes. After harvesting, you get a lot of other inert matter. We call it as inert matter. Double N, huh? Inert matter. So these inert matters are stone, mud, etc., etc. Even if you take 10 kilos of rice, you take rice, you will get stone, mud, maybe dead black color rice. All these will be there. So all these are called as inert matter. Right. Similarly, in the food, we can say various foreign substance. Foreign substance mean it is same thing as inert matter that inevitably end up in the food we eat and liquid we drink. There are a lot of inert matter. Even as I said, in rice, you have a lot of inert matter. One is this black color rice. In samba, you may get inside, you get some black color pieces of rice. So this is pest damage after the harvest or before the harvest, but it has been during the process, it has been added with that. You cannot separate. If you want to separate them, it is very expensive. Those are called as inert matter or foreign substance. That usually it is there in all our eating material and drinking material, usually. For example, this particular institute, Federal Defect Action Level, Food Defect Action Level, all right, they have found a criteria. They have given a level for insect damage of chocolate is 0.6 insect fragments. What do you mean by insect fragments? You are an expert on entomology. If you have insect, maybe a piece of leg, or piece of antenna, or piece of wing, right? A piece of abdomen, or piece of anything, any small piece of an insect. That is possible when you have a chocolate, right? When you have a chocolate which is damaged by insect, if you take the chocolate out, maybe for naked eye, very difficult to see, but you can see some remainings of the insect parts. Remainings of the insect parts, right? Those insect parts could be either of anything, right? Larva, eggs, or any body parts, or something else. As I said, anything is possible to see inside an insect damage piece of chocolate per 1 gram. So that is more important. So in 1 gram of chocolate, so you may have, this is 100 gram of chocolate, right? So this bar is 100 gram chocolate, but we are just measuring only 1 gram of chocolate. In that 1 gram of chocolate, this is the level of insect inert matters inside the chocolate. As an example, right? We didn't ask the question yet. Okay, so this is a statement, right? Now the question is, determine the mean number of insect fragments in 5 grams of chocolate. So initially it has been given for how many grams of chocolate. So we have given information for only 1 gram of chocolate. In 1 gram of chocolate, this much of insect fragments possible. But the question is, if you take a sample of 5 gram of chocolate, determine the number of insect fragments. So we want to find out the number of insect fragments, right? Second one, what is the standard deviation for that 5 grams of chocolate that has been put into as a sample? Let's look at these two problems. We will talk about little more applications later on. Suppose if x is the number of success in an interval of fixed length t, then the probability formula for x is given as such. So this formula is very important. So this formula is basically probability of x. So this capital X is the random variable, right? It is the random variable, right? X is the random variable. It's the number of success. When it's equal to a value of a small x, so that formula has been given as E. What do you mean by E? Anyone? How do you call this E? In your calculator, you can see exponential. E has a value exponential. Suppose, let's say, e to the power 1 is equal. Anyone? What is the value? What is the value of e to the power 1? 2.71828. It goes, but we'll stop with that. So this is the value of e. Have you seen something like this? Sorry. Log with a base e. This is called as natural logarithm. Arosha, can you? Who is having this? Is that Fatima or Arosha? Switch off your microphones. Logarithm. Natural logarithm, right? So this is the exponential. It's called as exponential, right? I will clear. Right. So that is exponential. Then it's depend on this component minus lambda t, right? Into this e to the power minus lambda t into lambda t whole to the power x. So this x is same as this x divided by x factor. What is x factor? X factor is given as x multiplied by, right, x minus 1 multiplied by x minus 2 and so on. It goes up to 1, right? For example, 5 factor is equal 5 minus 1, that is 4. So 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. So this is the answer for the 5 factor. So this x can take any value, right? 0, 1, 2, 3. probability value. Right. Now let's move to our calculations. Where, before calculation, we explain the terms. Yeah, the lambda. You see lambda here. Here also you have lambda. Where this lambda represents the average number of occurrence of the event in some interval of length t. So two things are important here. One is lambda. One is lambda. What is lambda? It is the average number of occurrence of the event. Average number of occurrence of the event. What is t then? T is the, because we have here t and lambda. Lambda is the average number of occurrence of the event. T is the length of the period, time, right? T is the length of the period, right? Length of the period or length of the interval, you can tell as you want, right? Right, we said about lambda and what do you call t. So this lambda into t can be rewritten. This lambda and t can be rewritten as mu. That means if this is a 1 unit, if this is a 1 unit, if we consider this as 1 unit, then we can write this too as mu per unit. This is mu, right? So that is why here we have set mu, right? Here also mu, right? So ultimately we can use this formula as well, the same formula, right? If you are not using for unit level, you can use this formula. Otherwise, you can use this formula. So probability of x when it's equal to simple x is equal e to the power minus u into u to the power x divided by x factor, right? We'll take the previous example and do it. X can take, small x can take any value 0, 1, 2, 3, 4. Right. We'll take a very practical example. We can answer for the previous one also, but we will take another example, very simple one. Take a hospital, right? A particular hospital. In that hospital, the birth rate, it's a very national big hospital. Birth rate is roughly 1.8 births per hour. So that means on an average, within an hour, we are getting 1.8 births. They have calculated, right? They have calculated based on past 5 years. They found that in an hour, doesn't matter what hour is, whether night or day or whatever it is, all 24 hours, right? So in an hour, the number of births are 1.8. Now, we can ask a question, what is the probability of observing 4 births in a given hour at the hospital, the same hospital? 4 births, right? So our question is, what is the probability of observing 4 births in a given hour? But already we know that in that hospital, the average birth is 1.8 per hour. Now we want to find out in an hour, what is the probability of getting 4 births? That is the question, right? Let's take x as the number of birth in a given hour, right? Let x is the random variable, which is giving the number of births in a given hour. So this is how we write the distribution. This is called as Poisson distribution. This is how we write the Poisson distribution for this example. X distributed Poisson with 1.8. This 1.8 is actually the mean value, the mean. So you see, this mean is given for per hour basis. Suppose if I put the same question in a different way, if I put the same question in different way, if I get 3.6 births per 2 hours, if I ask a question like that, if I get 3.6 per 2 hours, right? Automatically we can convert that as 1.8 birth per hour. 1.8 per hour, the number of births. So this is called as mean. This is called as mean, right? Right. Let's look at further. How about binomial distribution? How we say binomial distribution? X is distributed binomially with what? N and P. We have to give the N and P. Last time we said about N is the number of events multiplied by the probability. Right, now we can simply substitute the value as it is, because I said this is, sorry, this is mu, mu, what is the mu value? This is mu, right? So e to the power minus mu into mu, that is 1.8 to the power 4. Why 4? Our x, the question, the x is 4. So probability of x is equal 4, having 4 births, divided by x. So x is 4 factor. So if you get the answer, this is the answer. So this is the p-value. P-value in that particular hospital, it is the probability value obtaining 4 births in an hour. This is the probability of obtaining 4 births in that hospital. Right? Any questions? Any clarifications, questions? Yeah. So this is the answer for that question. Number of births, 4 number of births. What is the probability of having 4 number of births? So 4 number of births, the possibilities, this is the p-value. Right? Clear? Right. What about the probability of observing more than or equal 2 births in a given hour at the same hospital? So my probabilities, my question is here, more than or equal 2 births, right? Probability of x more than or equal to, right? So that is probability of x equal 2 plus probability of x equal 3 and goes up to infinity. Can we calculate this? Is it easy to calculate? No, it's not easy to calculate. Why? We can calculate up to the infinity. We'll have to substitute 1 by 1 of x, then calculate up to infinity as the x. So this is difficult. So, but we know the total probability is 1. We want to find out the probability of x greater than or equal to. This we can say 1 minus total probability of x equals 0 plus probability of x equal 1. What about probability of x equal 2? X equal 2 is already here, so we cannot include this. So you simply find out the probability of x equals 0 and x equal 1 and deduct from 1. If you do that, you will get the probability for this, right? So in simple form, so this is what we want to find out, probability of x, greater than or equal to, which is like this, right? Then I will erase what I have written, right? So what this is very difficult to go up to infinity number of probabilities to calculate. So that these things we can put it as 1 minus probability of x less than 2. So that is equal 1 minus probability of x equals 0, 0 and probability of x equal 1. So in simple form, we find out the probability of x equal 0. So that is the formula when x equals 0. So this is the formula for when x equals 0. So this is the formula for when x equals 1. So if you add these two values, so it is add these two values and subtract from 1, then you will get a probability this. So what you can say, this is the probability, right? This is the probability of getting, right, more than or equal to births in an hour in the hospital. More than or equal to births in an hour in the hospital. Right. Any questions? Any questions? Change of the size of the interval. Let's look at size of the interval. Earlier we have talked about interval for hour, 1 hour. Now let's look at how this interval can be defined for different occasions, right? Suppose we know that the birth in a hospital occur randomly at an average rate of 1.8 birth per hour. So that is the birth, right? What is the probability that we observe 5 births in a given 2-hour interval? So we can ask what is the birth what is the number of births? Let's say how we can observe 5 births, right? How we can observe 5 births in 2-hour interval. So it is same as asking question. Because if it is 5 birds for 2 hours, what is the number of birds per hour in simple term? Anyone? 5 birds per 2 hours. So if you say for 1 hour, what do you want to observe in 1 hour? How many birds?
2.5.
Yes, you just divide by 2.5. So sorry, divide by 2. So basically the question is, what is the number of birds? Oh, if the what is the probability to have number of birds as 2.5 in 1 hour? So that is the question. Simple, right? Because if the intervals are not overlapping, if intervals are equal, we can ask in a similar way. So that is why in the first assumption we said we'll have to be careful with intervals which are not overlapping at all. Right? So, well, if births occur randomly at the rate of 1.8 births per 1 hour, right? We can convert it either way. Either way conversion is possible. So 1.8 births per 1 hour interval. Then uh, uh, then the birth occurs randomly at the rate of 3.6 birth per 2 hour in the hospital. Right? We can do the questions in both ways. So let X number of births in 2 hour period. So Poisson, X is distributed. Now the question is different. The number of births in 2 hours. So Poisson distributed as a mu, right? Which is 3.6. Mu is actually lambda into T, right? So you can see here, this 1.8 is lambda. That is T. This is T. This is lambda. This is T. So what is the probability of having what is the probability of having 5 birds in 2 hours, right? What is the probability of having 5 birds in 2 hours? We are applying it directly, so that this is how you do it. You can multiply. This is the lambda again into T to the power 5. So X is 5. So divided by factor of 5. Right? So you will get an answer something like percentage 13, but it is 0.13768. This is the probability value of getting 5 birds in 2 hours. 5 birds in 2 hours. Right? So you can ask questions in different ways. 5 birds in 2 hours. Right? Just a second. Right. Any questions? Right. I will take sum of two Poisson variables. Sum of two Poisson variables. How we can say? Now we are taking two hospitals. Hospital A, Hospital B. In Hospital A, the average birth is 2.3 birth per hour. In Hospital B, the average birth is 3.1 birth per hour. Births per hour. Now the question is, what is the probability that we observe 7 births in total from these 2 hospitals, in both hospitals? Now we are asking, what is the probability of having 7 births in both hospitals together? Let X is number of births in a given hour at hospital A. Y is the number of births in a given hour at hospital B. That we have already the values 2.3 and 3.1. So we can say X is distributed Poisson with 2.3 and Y is distributed Poisson with 3.1. Now we can add simply the X and Y value. Why? Because the intervals are equal interval, 1 hour, 1 hour interval. So we can add this value. That is the specialty of this Poisson distribution. So to add this these two distribution X and Y, we add the value of these lambdas, lambda 1 and lambda 2. So now we can handle the question, what is the probability of having 7 births per hour on both hospitals? So now our new mu is 5.4. So e to the power minus 5.4 into 5.4 to the power 7, because here the number of births has to be 7. So 7 divided by 7 factor, you will end up with the answer as such. So that is the probability of having 7 births in both hospital in 1 hour. In 1 hour, that is the probability of having 7 births in both hospital A and B. Right. Some other conditions, the Poisson probability distribution function can be used to approximate binomial probability. So we can use that for binomial probabilities, provided the number of trials, right? We can approximate to the binomial distribution under certain condition. What are the conditions? The number has to be greater than or equal 100. So number of events has to be 100, very high. And this multiplication of this n and p has to be less than 10. P should have a lower value, that means. Right? When the number is high, the p should have a lower value. Then only you will have a value less than or equal 10. In other words, the number of independent trials, the number of trials has to be high of the binomial experiment should be large, right? So number of independent trials should be large, and the probability of success should be small. So in other terms, n should be large, right? N should be small. Right. Let's look at how to calculate the mean and the variance of Poisson distribution. Means and the variance of Poisson distribution. So mean of this mu, right? This lambda is here within that, right? If X is distributed Poisson lambda, then this lambda has to come inside. This lambda should go inside, right? Now I cannot correct it. Yes. difficulties. Something like this, right? Something like that, right? X distributed Poisson, lambda, then mu equal lambda. These are same because when t is equal 1, yeah, I said mu is depend on lambda and t, right? Mu is, sorry, lambda and t. Mu is depend on lambda and t. If t is 1, then mu is equal lambda. So that is mu is equal lambda. Then the variance is given by lambda. Only one parameter here. So the lambda is the parameter in Poisson distribution. So the standard deviation is square root of lambda. Very simple, right? Can you all see? I have some technical problem, so I'll come to you soon. Take 2 minutes break. Huh? Take 5 minute break. I will come to you. Okay, we will start with continuation of Poisson distribution. We have some problem with the operators, so we will, without wasting time, I can use the slide as it is. Right, we will continue with that. Okay. Mm, uh, right, in Poisson distribution, lambda is the most important parameter. Uh, Suppose, let's say, when you have probability for a Poisson distribution, suppose, let's say, if the value for the mu is 1, how the distribution looks like if the mu is equal 1, right? So if the mu is equal 1, how the distributions looks like. If the mu is 1, the distributions looks like as such. How do you call this distribution? Is it symmetric?
Right skewed.
Right skewed, yeah. Well, so we can call this as a right skewed distribution. Right. So this is when the lambda or mu is equal 1. Your lambda and mu are same when t is equal 1. So mu is equal 1. Let's look at another example. When my pad is going. Some problem with the pad. Okay, I will not use the pad. Right. So this is right skew. Then what about this? Mu is equal 3. The mu is equal 3. Mu is equal 3. So now you see, if you draw it, so you can draw like this. Still, it is slightly right skew, right? If you go further, I use this. I think I have some problem. So Some technical problem. So I'm just putting it on the direct screen. So we'll, without putting the slideshow, we can talk about it. I'm not going to use the pen. Something wrong with the pen. So if the mu is, let's say 1, this is how the distribution looks like. So as I said, this is goes to the right skewed, somebody said. So again, if the mu is higher, mu is 3, then you get some more or less a distribution, nice distribution, but still it is right skewed. Now, if you increase the mu further, what is happening? If you increase the mu further, what is happening? Can somebody tell me? This is mu is equal 7. Now mu is equal 15. What can you say about the distribution now?
Symmetry.
Yeah, it is going more or less symmetric. So what we can say is, when the mu is very small, it is a right skew, then it goes on symmetric, right? When the mu increases, it goes on symmetric. So that means most probably we will learn about mu distribution. It is called as normal distribution. Normal distribution is a symmetric distribution. So if you increase the mu, the size of the mu, then it is approaching to the symmetric distribution, which is called as normal distribution, right? Most probably we don't have time today, so that we will discuss that later. So it is moving towards normal distribution. An example here for the Poisson distribution. This is something to do with this radiation, emitting radiation, alpha particles for a given interval, right? 8 minutes of interval, roughly about 7.5 seconds of interval. How much emission takes place? Number of detected emission 0 is 57 times emitted for that interval. So number of detected is 1. How many times numbers detected 1? The number of time detected, frequency is 2003. So likewise, you have some values, numbers detected. So basically, the alpha particle emissions detected from a polonium source in equal distance of time, right? So this is if you have some calculation. So this is the number of time detected 0. 57 times they have detected of the event 0, event 1, event 2, and so on. Then this is the frequency, this is the x into f, expected proportion. Expected proportion is basically this is the probability, right? 57 57 divided by total number, yes, 2608. Likewise, this is the expected probability, right? Based on that expected frequency if Poisson distribution, right? So these are the expected proportion if we are using Poisson expected frequency, expected proportion and frequency. Just some example, right? So the mu is mu we can calculate based on this. Right. The last distribution that we want to discuss for the day is called as uniform distribution. All right, distribution. It is considered uniform distribution, sometimes called as rectangular probability distribution. Sometimes it is called as rectangular probability distribution. It is described by the function. This is the function because it is an area of a rectangle. For example, area. This is the probability. This is the event. This is the total probability. This is the area of total probability. So for a given event, the probability is find out using this formula 1 over b minus a. B is the highest point, a is the smallest point of the x-axis, right? So the total area we consider always as 1, right? Total area we consider as always 1. So the probability is in between 1 and 0, where this x value can be any value in between a and b, upper value and the lower value. We call it as upper value and the lower value. So if you multiply this area, total area, this if you multiply from this to here, x value into probability value, it will give a value 1. Therefore, area is the one which gives the probability. Width into height. So this is the width. Sorry, this is the width into height. Height into width, which gives the area. So the height is this much, width is this much. So width is b minus a. B is the higher point, a is the lower point. So b minus a is the width of this multiplied by the height, right? Height, let's say x or whatever the y value is equal 1. So normally this is the formula that we use. Right, we will look at an example. So this is an example. The amount of gasoline, that is filling station, that petrol shed, gasoline sold daily at a service station. Gasoline means it is another name of petrol. Is uniformly distributed with a minimum of 2,000 gallons and a maximum of 5,000 gallons. So on a daily basis, that petrol shed selling 2,000 gallons to 5,000 gallons. Minimum is 2,000, maximum is 5,000. So 2,000 to 5,000 is the maximum and the minimum. Right, now the question is, what is the probability that the service station will sell at least 4,000 gallons on a particular day? At least 4,000 gallons. So at least 4,000 mean mathematically, algebraically, we can say probability of x having more than or equal 4,000 gallons. more than or equal 4,000 gallons, right? More than or equal 4,000 gallons. So if it's so, 5,000 margin is here. So this is 4,000. Let's say this margin is 4,000. So we want to find out this area, the blue color area. We want to find out the area of that, which is giving the probability of that. So in other term, probability of x is greater than or equal 4,000, which we multiply this width, right, into height. Height is 1 over 3,000. Why? Because it is the difference between these two, 5,000 and 2,000. The difference is 3,000. B minus A, 1 over B minus A, so which is 1 over 3,000. So height is 1 over 3,000. So if you want to get the probability, that is 5,000 minus 4,000, that is the width, right, multiplied by 1 over 3,000, you will end up with 0.333. So that means your probability of selling at least 4,000 gallons on a particular day in this particular station will be 0.333. You can say 0.34 in the closest approximation. Right, I think we have some problem in technical problem, so that I cannot continue with the slide. Right, any questions?